First, we will draw the energy band diagram for metal, insulator, and semiconductor separately, which we have also drawn in first unit. Now, we will join all these three energy band diagrams along with two vertical lines which simply represents the junctions. There are few parameters you should know. The first is work function. It is the average amount of energy that an electron requires for complete detachment from the parent material. Whenever there is a concept related to average electron energy, then we are supposed to consider the Fermi energy level. So, we have metal, oxide, and semiconductor work function, which is the difference between Fermi energy level and vacuum energy level. The second parameter is electron affinity, which is the amount of energy released by an electron to form an anion from a neutral atom. This is the difference between conduction band energy level and vacuum energy level. None of these parameters are directly involved in the analysis of MOS capacitor. The important parameter is difference between metal and semiconductor work function. This parameter is directly involved in the analysis of MOS capacitor. Sometimes in GATE, ISRO and ESE prelims, questions are asked from MOS capacitor which actually does not use any concept of MOS capacitor. Like for example, assume that the shown 4 parameters in the energy band diagram are provided to you and you are asked to find metal to semiconductor work function difference. There is no direct formula. You have to simply observe the energy band diagram and do some manipulation to get metal to semiconductor work function difference. Like here, the metal to semiconductor work function is equal to electron affinity of the semiconductor plus conduction band energy level minus Fermi energy level of the semiconductor. Consider another case in which rather than providing you the Fermi energy level of the semiconductor, valence band energy level is provided. You still need to find the Fermi energy level of the semiconductor. So far, I have considered only intrinsic semiconductor. So, it will be better if we change the symbol for Fermi energy level from EF to EFI, where I is representing intrinsic semiconductor. In the first unit, we have found the formula for intrinsic Fermi energy level with respect to effective density of states in conduction band and effective density of states in valence band. We got another formula for intrinsic Fermi energy level with respect to effective mass of free electrons and effective mass of holes. If these parameters are provided, then obviously you have to use the formula, but if effective density of states and effective mass are not provided, then assume yourself that intrinsic Fermi energy level lies exactly in the middle of conduction band energy level and valence band energy level. I have told you earlier also, and again I am telling you, tricky questions of this unit will be requiring the concepts of first 2 units. So, it is very important for you to revise the concepts of unit first and second, otherwise you will not be able to solve the questions. Anyways, it might be clear to you by now that all these parameters which are represented on the diagram are important only for finding the metal semiconductor work function difference. But few parameters can be removed so that the energy band diagram becomes less congested, like valence band and conduction band energy level of metal, electron affinity of metal, work function of oxide, and the Fermi energy level of the oxide. All these parameters will not be used in later lectures, so they can be removed from the energy band diagram. For simplicity, we sometimes also use modified work function, where we assume the conduction band of insulator coincides with the vacuum energy level. Modified work function of the metal is the amount of energy that is required to inject an electron from the metal into the conduction band of oxide. We can define metal modified work function as metal work function minus the insulator electron affinity. The same way, semiconductor modified work function is defined. There is no difference whether we use modified work function or the work function, as the difference between metal and semiconductor work function remains the same. There is another way by which we can simplify the energy band diagram. Rather than moving the vacuum energy level downward, we can also move the conduction band energy level of oxide upward. By doing so, we are preserving all the parameters in their original form. We simply consider that there is an oxide which is having zero electron affinity. Authors of different books have used different methods for simplifying the energy band diagram. However, in all the later lectures, I will be using this diagram only, where the electron affinity of the oxide is considered to be zero. So far, we have taken intrinsic semiconductor. What if the semiconductor is doped? Consider a semiconductor which is p-type doped. If you carefully observe, then you will see that the electron affinity of the semiconductor will not change, but the work function of the semiconductor changes when doped with acceptor impurities. Here also, different sets of data can be provided to you, and you might be asked to find the metal to semiconductor work function difference. You may have to use the formulas which we have derived in the first unit. For different devices, the conditions for ideal behavior changes. The ideal condition for MOS capacitor particularly includes two major conditions. We can see there is a difference between Fermi energy levels of metal and semiconductor. Our first assumption is there is no such difference, which will ultimately result in the work function difference between metal and semiconductor to be equal to zero. And the second condition is the oxide is free from trapped charges, meaning that there is no charge present inside the oxide. These conditions for ideality of MOS capacitor are very important and you should learn them.